All right, so we already talked about correlation earlier in these live lessons, but back then we didn't have enough statistical understanding under our belts to talk about statistically significant correlations. So we're going to fill that gap in now. All right, so let's quickly review some stuff that we already learned earlier in these live lessons, but just so we have everything top of mind. So if we have two vectors of the same length, x and y, where each element of x is paired with the corresponding element of y, so this is just like in our paired sample t-test, there needs to be a corresponding element in x and y, like an Alzheimer's patient who got a treatment on one day and a placebo on another day. So that's an example of a pairing. So if we have that pairing, then covariance provides a measure of how related the variables are to each other. So here's how we calculate covariance. We already talked about that earlier on the whiteboard in a lot of detail, so I'm not going to do that again. You can refer back to that video earlier in these live lessons if you'd like a review. Recall from back then that a drawback of covariance is that it confounds the relative scale of two variables with a measure of the variable's relatedness. So we talked about how correlation builds on covariance and overcomes that drawback by rescaling, so thereby measuring only the linear relatedness between x and y. So correlation is much more common because of that difference. It was developed largely by Carl Pearson in the 20th century and is often denoted with r, a lowercase r, or the Greek letter rho, and it's defined by this formula here, again, one that we went through on the board in a lot of detail already earlier, so I'm not going to go through that level of detail again now, but just to quickly remind you that we have covariance in the numerator, and then we divide by the product of the standard deviation of both of our vectors, x and y. So something that we also did earlier in these live lessons was load the iris data set and then grab the sepal length and petal length and put those into separate vectors. So we grab those columns, put them in the vectors. I'm going to change the Seaborn style here to a dark grid and then create a scatter plot of the two values against each other. We saw this already earlier. So we're going to need our n, we're going to need our x bar, our y bar, and then we can iterate over each of the instances in our data set, each of the pairs, to calculate the numerator for our covariance. And then we can calculate the covariance here by dividing by n. And finally, we can get our Pearson correlation coefficient, r, by dividing by the product of our two standard deviations. So all of that we already covered earlier when we were talking about probability. Now, the last step is that we want to actually determine a p-value. So when we have this kind of correlation, when we get a Pearson correlation coefficient of 0.87, is that statistically significant? Is there a statistically significant relationship between sepal length and petal length? Well, now we have all the tools at our disposal to answer that question. So in order to get a p-value, we're first going to calculate a t-statistic, a t-value. And we can get that with this formula. So Pearson uncovered this a while ago. We're not going to dig into the detail of every little thing that's going on here, but this is the formula. We've got our r in here twice. So we've got r squared in the denominator, and then we multiply by r here, that value. And we've got n, our number of samples, in the numerator before we take the square root. So altogether, that allows us to calculate our t-statistic, which comes out to 21.6. And yeah, I know that that's a big t-statistic, so I'm confident it's going to be very statistically significant, and we can convert it into a p-value using the p from t method that we created earlier in this notebook. So we just pass in our t-value. We have n minus 1 degrees of freedom, again, because remember from that degrees of freedom conversation that one of the values amongst all of our data points can't vary freely if we know what the correlation is. And yeah, this comes out to an extremely significant p-value, 1 times 10 to the negative 47. So that's a negative log p-value of very close to 47. And that is way, way, way below our significance threshold of 0.05. And so it confirms that the sepal length of irises is extremely positively correlated with petal length. Now, all of the above can be done in a single line of code with SciPy's Pearson R method. And we actually used this already earlier. And back when we were using it earlier, I said, ignore this second argument here. But now you understand what that is. You know what p-values are. You know where they come from. And so now you understand that not only do you know what the correlation between two terms means, but you know that it's very statistically significantly meaningful in this case. And for reference, after having looked at this very statistically significant relationship, let's also look at a correlation that is not statistically significant. So where our correlation, our R value, is close to 0, as opposed to being close to +1 or -1. So let's have a look at sepal length versus sepal width for our iris data set. We did look at this earlier in the probability context. And now we can feel comfortable passing those two vectors into our Pearson R method and understanding that, yes, there is a modest negative correlation of 0.12, but that is not statistically significant. So this is higher than 0.05, and so it means that we would say that this very slight relationship between length and width is not meaningful.